this lesson, we'll explore the available analysis types and the concept of topology optimization. Before starting the analysis, configure the analysis parameters. For the majority of analysis types, you can select the solving algorithm and specify the amount RAM allocated for the analysis. The available parameters depend on the analysis type. For natural frequency analysis, for example, you can also specify the number of natural frequencies to extract. After the analysis is complete, we can evaluate the results. Results can be visualized as column map showing stress distribution, displacement distribution, and other quantities. By enabling additional display options, you can overlay the undeformed shape of your structure alongside the deformed and color-coded result, as shown in the image on the right. These result images are scaled, and a scale bar is displayed alongside each one. You can adjust the scale factor to improve the clarity and readability of the results. When running a buckling analysis, APMFEM provides a table of buckling safety factors. For this assembly, we can see that the buckling safety factor for the first buckling mode is 95.5, meaning the applied load could be increased approximately 95 times before the structure loses stability. This indicates that the structure has a very high stability margin. The natural frequency analysis results in APMFEM include a table listing natural frequencies in both radians per second and hertz. The table also includes oscillation periods and model masses, which help you determine the predominant direction of deformation for each mode. Looking at the first row of the table on the screen, we can see that the model mass participation factor in the x direction is 23.6%. This means that 23.6% of the total assembly mass participates in motion along the x-axis for the first mode shape. APMFEM is also capable of performing steady-state heat transfer analysis in the base version and transient heat transfer in the professional version. APMFEM allows you to define all required thermal boundary conditions. This analysis can be performed independently if you need to evaluate the temperature distribution within your structure, or you can first run a thermal analysis and then incorporate its results into a subsequent static analysis. If your component has a wall thickness that is negligibly small relative to its overall dimensions, such as pipes, vessels, or equipment housings, you can analyze it as shell model. So the total node count of the finite element model will be significantly reduced since flat shell elements require fewer degrees of freedom than solid elements. This reduces both computation time and memory usage while maintaining the required accuracy. To transform an original solid model into shell model, Compa3D provides dedicated tools for this purpose. The three primary tools are mid-surface, delete faces, and copy objects. Since APMFEM is a Compa3D app, you can open your model in Compass, convert it to a shell model using one or more of these tools, and perform analysis using APMFEM tools. Another important APMFEM capability worth discussing is topology optimization. Topology optimization is computational methodology for determining the optimal material distribution within a design space, subject to defined constraints, loads, and boundary conditions. The result is an optimized geometry derived from the original design space that satisfies all specified design requirements and constraints. We can account for loads and define parameters to maximize or minimize, such as stiffness, mass, or displacement. Topology optimization analysis can be computationally intensive and may require significant processing time. However, the result is structurally optimized geometry. Topology optimization can reduce the mass of load-bearing structures by 30–40% without additional manufacturing technologies and by up to 70% when advanced manufacturing methods are employed, all without compromising structural strength and stiffness. Alternatively, structural strength and stiffness can be increased by a factor from 2 to 5 without any increase in mass. The slide shows an example of topology optimization applied to a structural component. Finally, once all analyses are complete and results have been reviewed, you can generate a comprehensive analysis report and export it in PDF, XML, or HTML format.